Hello everyone, I am Paul Golter, studying technical directing at the Animationsinstitut in the last year. A couple of years ago I started out as a 3D generalist and quickly noticed that I'm always drawn to the technical topics. I transitioned to become a pipeline TD, and now I'm developing tools and streamlining workflows to empower everyone to do their best work in the most efficient manner. During my practical year, I had the chance to work at the Blender studio to support the production of the open movie Sprite Fright as a pipeline TD. In the next 10 minutes, I'm going to show you what I have been and will be working on here at Filmakademie. I'm going to talk about our Diploma project and give you some insights on how we use USD in our pipeline. I will also introduce you to my research project, the Asset Encoding and Transformation Framework. Let's go. Our Diploma project Underwater is an IP with two formats, a film and a game. The style will be dark, gritty and quite photorealistic. It's going to play in a huge world with one catch. The sky is not made out of clouds, but an ocean with big ancient creatures swimming in it. From a technical side, this project comes with a couple of interesting challenges. First, we have the two formats, a traditional offline rendering short and a game running in real time. We also have quite a big team for a student production, and we have this huge open world that needs to be set up and built in an efficient manner. We use ShotGrid as our base pipeline framework. My goal for this project is to set up the entire production of the film in USD and share as much as possible with the game. Except for animation, which will be done in Maya, we are using Houdini as our main USD authoring tool for almost all the other production steps. While there are more and more resources out there that explain USD concepts, there are only a few talking about structuring USD files on a bigger project level. So let's have a look at what we came up with. First, let me explain how we structure our USD assets. We start with an XForm primitive called root with the component kind. Underneath, we have a geo, proxy and materials primitive. As these are purely used for organizational purposes, they share the primitive type scope, which prevents transforms from being applied. Note that only the root primitive is an XForm, which should be used when transforming the asset. We also have two default variant sets, geometry and material, which are stored on the root primitive. Each default variant is called main, and when artists want to add a shading or a geometry variant, they already have a set prepared for them. It's really useful to have the variant sets named in a standardized way and store them on the asset root primitive so pipeline tools and scripts can easily make use of that. I want to point out that the asset root primitive is inheriting from a class primitive. Most of the time we don't touch the class primitive anymore, so this won't make a difference. But setting it up that way gives us the option to broadcast changes on all assets in a USD scene. We could, for example, do some shading, attribute or variant overrides for all assets in a scene by modifying the class primitive structure. Last but not least, a quick note why we decided to name the asset root primitive root instead of giving it the asset name. This was inspired by the USD example dataset ALAB by Animal Logic. In USD, primitive paths are used to uniquely identify a primitive. Overlaying or adding another primitive at the same path leads to a calculated result by the USD composition engine. For that process, it's very convenient if the structure of all assets and shots is simply the same. And when importing assets in, let's say, a layout scene, you would usually use a reference which attaches the USD layer to a target primitive path, so you don't run into name clashes. Our shot layers are pretty much set up in the same way, except that some primitive names and some primitive kinds are a little bit different. But the overall concept is the same. Let's zoom out a little bit and look at how our USD layers are stored on disk and how they reference each other. Our team is working on a shared network drive, which is a common studio setup. We run a pretty standard folder structure with an asset and shots directory hierarchy. With USD, one extra folder joined in, which we call the stage folder. This directory hierarchy only contains USD files and nothing else. In this directory, we basically have a USD representation of our whole project. If we jump a couple of folders down, we can see that each asset and shot has one USD file that represents that entity with all the layers that contribute to it. When artists would reference an asset into a scene, they would point to the asset USD file, for instance. The different layers that contribute to this USD file are stored in a subfolder respectively. This department USD layer points to another USD file, which is the actual versioned output of the artist's working scene. If an artist publishes a new version of their task, we only have to update this one pointer, and the asset or shot.usd file has the latest state. From a pipeline perspective, this was a switch from a pull to a push pipeline. Earlier, we would have some sort of asset updater that would exchange the reference of an asset to the latest one. With USD, we can now change the path a USD layer is pointing to during the publish process already. That way, our assets are always in the latest state, but we can still roll back if we need to. One challenge with this workflow is rendering. Even though our asset and shot.usd files are essentially always live, we don't want the images on our render farm to change from one frame to another because something was updated in between. To essentially lock or prevent a stage from changing when it was sent to the farm, we can simply create a copy of the whole stage directory, as it is only a couple of megabytes in size. It is kind of stupid, but it works. The prettier way would be to use a custom asset resolver that locks each layer version when it is running on the farm. To wrap up the USD part of this presentation, I want to quickly show you some tools that are already in use right now. We are currently in the previous phase in which we want to work fast and quickly iterate. With USD, we could easily set up a sequence-based approach in which artists can do layout for all shots in one sequence by simply specifying the shot name in our publish USD HDA. The publisher then exports and moves the USD files to the right places and even uploads an automatic play blast to that shot to ShotGrid, ready for review. The last part of this talk is going to be about my research project here at Animationsinstitut. As technical directors, we have to come up with a topic and code a prototype to it. I decided to develop an asset encoding and transformation framework. This idea is based on some research that has been done in the SOURCE project. SOURCE is a collaborative EU research and innovation project. It stands for Smart Asset Reuse in Creative Environment. It covers a couple of topics to increase efficiency in the creative sector. Bigger areas are light field, semantic animation and crowds, as well as asset pipeline. Encoding and transforming data happens all the time in a pipeline and is therefore a very integral part. I really like the idea of having a dedicated engine whose purpose is to manage that process. The plan is to build a Python framework with which users can define recipes. A recipe defines how to cook a product out of certain ingredients. While recipes can be ultimately very simple, for example, convert an Alembic file to a USD file, they can also get quite complex. For example, based on some shot staging data on ShotGrid, cook me a blend file that has all the assets linked in. Or cook me an image sequence, which is a turnaround, based on an input USD file. The framework itself should provide the functionality to register recipes through a common standard. The actual implementation of the recipe is done by the user or the TD. Based on a set of input data, the framework can show recipes that can be cooked with that data. By defining recipes, users can essentially encapsulate workflows that produce expectable results. And this opens up the opportunity for automation, as recipes can be applied to a big batch of input data. In a pipeline, this framework could find application in the publishing process. During a publish, it could be very useful to automatically run a couple of recipes on the published data to create different representations of it in one go. It can also be a powerful tool as a layer between an asset library and a consumer. For storage reasons and to only have one ground truth, it makes sense to store an asset in a single format in a library. The asset encoding and transformation framework could run the correct recipe to provide the consumer the format that they need for their workflow or application. Another interesting concept to look at could be how to chain recipes together and create dependencies between them. That way, users could change multiple workflows together and create very complex automations. Currently, I'm still in the design phase for this project with some first lines of code written down. The first step will be to create a system that allows users to write and register their own recipes, which are detected by the framework. The framework itself will come with a couple of example recipes, which should make it easy for users to understand how to write their own. Thank you so much for the attention and enjoy the rest of FMX.